Welcome everyone to today's A16Z Crypto Research Seminar. Very happy to introduce Victor Shoup, Professor Emeritus at NYU, and these days also working at Offchain Labs. Victor's well known for lots of different results in cryptography over many years, but he's actually been working some in consensus lately, and that's what he's going to tell us about today. So, Victor.
Thanks for the introduction. Thanks for inviting me to hang out here for a couple of days. So yesterday, Christian gave a nice overview of a lot of consensus problems, kind of flying above the mountaintops. I'm going to be like working out in the backyard in the tool shed on some little tiny things and show you around some things I've been looking at lately. So I'm going to be talking about reliable broadcast. Just quick survey. How many people here know Braca's broadcast? Okay. So this will be a self-contained talk, but I'll maybe go a little bit faster through some of the Braca broadcast stuff. So reliable broadcast is kind of a very special case of consensus, and it's used in consensus protocols such as the DAG-based consensus protocols. It's a component there, as well as others, and I'll talk more about that later. So what's the problem? So we have n parties, P1 through Pn. They're connected by, I'll just assume, authenticated channels. I won't really be using any other cryptography today. So they're connected by point-to-point channels. And communication is asynchronous. So there's no notion of time. There's no upper bound on how long it will take messages to be delivered from one party to another. And really, we'll be assuming here that the adversary totally controls the network when a message is delivered, and even if it's ever delivered. But he can't alter the contents of the messages. That's where the authentication comes in. In this setting, so we have some number of corrupt parties. At most, T can be corrupt, and we'll assume that's strictly less than n over 3. And that's the best you can hope to do in this space. One of the parties is going to be a designated sender. So we're just going to be looking at one run of the protocol where there's one designated sender. He's trying to send a message to P1 through Pn, right? So if the sender was a good, honest party, he could just send his message to everybody and we would be done. But if the sender is corrupt, he might choose to send one message to some parties, another message to other parties, and maybe not send any message at all to some other parties. So we want to kind of force a corrupt sender to send the same message to everybody. And of course, a corrupt sender could just be sleeping the whole time and do absolutely nothing. So in which case, we have to be a little bit careful how we define things, right? So maybe no message gets delivered to anybody, but if any message does get delivered to some parties, then all parties should get the same message. So there's a correctness property that says that all honest parties that output a message should output the same message. And if S is honest, that message should be the one that S wanted to send and not some other message. And then there's kind of a liveness or completeness property, which says the following. If, on the one hand, if the sender is maybe corrupt, but if any honest party ends up outputting a message, or if the sender is honest and actually runs the protocol, then eventually all honest parties output a message. That's the completeness property. And eventually is a technical term. There's no notion of time. So one way to think about it, and I have arguments with Christian knows very well. I have arguments with people, not with Christian, but we've had arguments with various people about how you define any of this stuff. In all of these protocols, there's going to be like a finite number of messages that are ever transmitted. And eventually just means that if there's no other messages that have been protocol messages that have not yet been delivered, then at that point in time, all honest parties should have output a message if that's what they were supposed to do. So that's what eventually means. This is your lecture on Braca broadcast if you've never had one before. I told you I'm going to be working out in the tool shed, looking at little wrenches and whatnot. So we'll start with Braca, a classic protocol. So I'll kind of go through some details because they kind of matter. So here's my sender. He's going to send a message to all parties. So he's disperse his message. So this is what he's supposed to do, right? Now, every party, I guess including the sender is also involved here, is acting as a receiver. So here's the logic for the receiver. They're just going to go through a loop forever waiting for different conditions to happen. So the first condition that will trigger some action will be, well, if that party receives this dispersed message that the sender sent up here, right? And if he hasn't done anything before, so this variable is still false, then he's gonna remember that he's gone through this step before, and then he's gonna echo what he received to all other parties. So the sender sends a message to each party then echoes it to every other party. And they're only gonna echo a message once, never more than once. Okay, then, so that's step one. Step two is if I, as a party, receive the same echo message from n minus t distinct parties, I'm going to vote for that message. And sometimes this is called a ready message, but here I'm calling it a vote. So I'm going to record that I voted, and then I'm going to echo the message all over again to all the other parties, this time labeled as a vote, and that's what I do. So actually there's two ways that we're going to vote for a message here. One way is if I see like n minus t echoes of the message, I'm going to vote for it. Now, why the n minus t? For those in this don't work in this asynchronous space, it's kind of like there might be t-crashed parties, right? So, and there are n parties altogether. So I can't afford to wait for more than n minus t parties. So in these protocols you see all the time, wait for n minus t of this, wait for n minus t of that. So that's why you see those. So there's two different ways that you can vote for a message in Braca. One is you saw a whole lot of echoes. The other one is that you didn't see them, but you're going to jump on the bandwagon anyway because you saw t+1 parties voting for that message. And this is a nice little device that ensures that ensures the completeness property, really. That's why it's there. Then finally, if you receive n minus t distinct vote messages, you're going to deliver this as your output. So that's the whole protocol. Question?
Comment. The last n minus t could be 2t+1.
I haven't thought. Yeah. Or it could be this crazy thing with lots of floors and ceilings in it that you tend to write in your paper.
I don't do that.
You don't do that anymore?
No, I never do.
You did.
I never want to do that.
Papers. You had
I have bigger than n plus t over 2.
N plus t over, yeah, with a ceiling or a floor or something.
No, strictly bigger than n plus t over 2 gets rid of the ceilings and the floors.
I don't want to have to separate you guys.
Okay, so if I had a little bit longer to talk, I would like walk through all these. I want to like walk through very quickly like how you would analyze this thing, and I want to just focus in on one property, and then I'll skip over the rest. So let's call this the many echoes property. So if some honest party ever votes for a message n, then some honest party must have received at least n minus t echoes of m. But remember, you can vote in two different ways: jumping on the bandwagon, or if you voted because you saw n minus t echoes, then yes, we're done, right? But so otherwise, you argue that the first party who voted for m must have not been jumping on the bandwagon because one of those t+1 honest parties must have been honest, and so there must have been some point in time where some honest party voted by seeing many echoes, and so that's what guarantees the many echoes property. And then from there, so that's one property. Then from there, you can argue unique votes, so no two honest parties ever vote for different messages. And here you just wave the magic wand of quorum intersection to say, well, you can't have like many echoes for two different messages. So, and then there's the completeness properties, which I think I'll kind of skip over, not to go too deep into the weeds here. There's a completeness property, which is, and then there's validity property, which says that if the sender is honest, then eventually all parties will output the sender's message. So that's that. Okay, so let's talk about message and communication complexity. So let's define terms. The message complexity is just the total number of messages sent from all honest parties to any party. You add them all up, and you can see for Braca, there's n squared messages. Everybody sends a message to everybody, so there's n squared messages. Okay, that's fine. Communication complexity. So the typical way you define communication complexity is you look at each party and ask how many bits did they transmit to all other parties, and then you sum that up over all honest parties, and that'll give you the communication complexity. But I'll come back to talking about like what's the right way to define communication complexity a little later. So for Braca, you can see that everybody echoes the message to everybody else. So it's n squared times the message length. So that's pretty easy to see. Can we do better? Yes. So Christian looked at this problem and noticed that we can use erasure codes, which I'll be talking about a little bit later, to get the communication complexity down to big O of message size times number of parties, plus some term here that doesn't depend on the message size. And this is optimal in some sense, in the sense that, well, the message has to be delivered to everybody. So if you look at like download message complexity, every honest party is going to have to download the message from somewhere. So those bits must have come from somewhere. So the overall message complexity is going to have to be n times the message size, just to get the message out to everybody. So that was so that's a nice result. And then there have been some improvements. Oh, by the way, so here lambda in this expression is going to be the hash output length of some hash function, so 256 bits. And there's this log n term here, which comes from Merkle trees, which I guess everybody knows about Merkle trees. I was told that that's a safe bet. Okay. So that was back in 2005, some nice progress. And then also sitting in the audience here is Saurav, who did some more work on this. And he focused in on this term here and said, do we really need this log n term? And he said, no, we don't. So we got rid of this log n term, which for so you can say, well, when is this important? It's important in applications where m is around the same size as n. So in that regime, this gives you an improvement. Abraham and Asharoff also looked at this problem and noticed that, well, it's the same results, but what's different is this is statistical security. So this lambda here is, for Saurav's result, is again the output of a hash function, the output length of a hash function. Here, I'm kind of paraphrasing Abraham and Asharoff a little bit. I think this lambda is just a statistical security parameter. There's different ways of stating the result, but I think this is a fair way of stating it. So they don't need any cryptography. I said we don't need cryptography besides authenticated channels, but here I just snuck in a hash function. Here they get rid of any cryptography again, if that's what you want to do. In this work, I'm going to be thinking about what is this big O constant here on the m times n term. Because if I have like really huge messages, like many megabytes, and my network is small-ish, say a few dozen, up to 100-ish nodes in the network. I mean, the only thing that's going to matter is, in terms of communication complexity, is the constant, is this term here. So not to be critical, but I mean, this, worrying about this term is important in some applications, but not in others. So in the application where this message might be very big, and certainly like in certain blockchain projects where you've got several megabytes of transactions being disseminated by a leader, these types of techniques for getting like. At my last gig at Dfinity, I tried to convince them to implement some of this stuff, and they were complaining about this factor of 3 that you get off the bat just by using erasure codes. So if you look at all of these works, if you look into the constructions, you're going to get a cost of at least 3 times the message size times the network size, plus some lower order terms. For the rest of this talk, I'm going to just be talking about how to lower this constant. So hopefully you'll find that entertaining and interesting, but that's all I'm going to be doing. So I said I was going to be messing around in my tool shed in the backyard here, so that's all I'm going to do. So my colleague Thomas Locher, who's still at Dfinity, raised this question, which is interesting because I mentioned this problem to somebody else recently, and they assumed that this 3 was just like some universal constant, and nobody had ever even thought of like is this the right like. Yeah, so Thomas got a result and got the 3 down to a 2, and then we joined forces and we got it down to 1.5. Okay, so yeah, so it's a pretty modest goal here. So that's what I'm going to talk about. But if you haven't seen like how these erasure codes work and everything, hopefully you might learn something useful. So let's talk about erasure codes.
Is there any lower bound bigger than 1?
Well, no. So that's like one of the open questions, is to get a lower bound on this. So we think the lower bound is 1.5, and Thomas has a result, but in a very limited model. So it's not really it puts too many constraints on the protocol. So under some not very realistic constraints, you can prove a 1.5 lower bound, and we kind of feel in our bones that's the answer. But it's a nice problem. So that's actually, if I can get any of you to work on this and solve it, that would be really cool. So let's talk about erasure codes. They're nice to know about anyway. So I'll walk through the whole kind of how you do all of this and then how you get the improvements. So we're going to start out with the 3x results. So what is an erasure code? So if I have this is like an n minus 2t out of n erasure code, means that I'm going to take my message m, encode it as a vector of n fragments. And the property is that the second parameter here is the kind of the reconstruction threshold. So in this case, any n minus 2t fragments can be combined to reconstruct m, right? And you can do this using Reed-Solomon, which is just a fancy name for polynomial interpolation, right? So this can all be done. How big is each fragment? Well, you're basically taking the message size and dividing it by the reconstruction threshold. That would be like the degree of your polynomial. So just taking your message and chopping it up into coefficients of a polynomial, and this is basically how many coefficients you have. And so this will be, I'm assuming here that t is, say, around n over 3. So in this case, fragments will be of size, m divided by n times this factor of 3, which is where the whole 3 comes from in this business. So the idea now, we can kind of bolt this idea onto Braca very easily. And there's a number of different ways of doing this. I'll show you one that's anyway kind of interesting. So the idea is this. So the sender S starts by encoding M as this vector of fragments. And then he builds a Merkle tree whose leaves are the fragments. And let's say R is the root. We're going to run Braca basically with the root in place of the message. So the root is nice and small, so we can do this. But we make a few adjustments. So here are the adjustments we make. In the first flow of the protocol is this disperse phase. So we're going to disperse the root of the Merkle tree. But the sender is also going to send to each party pi his fragment fi along with the Merkle proof or the path so he can validate that this is really the opening of this vector commitment at the ith position, right? So he's going to like piggyback these fragments in the first flow of Braca. Each pi is going to echo in the echo. He's going to echo the root of the Merkle tree, and he's also going to echo his fragment along with its proof. Well, he's only going to do this if the Merkle proof is consistent with the root that he received as a part of the disperse. The votes are going to work the same way as before. At the last stage where we output, right, we're going to collect n minus t votes and then output a message. So what we're going to do is the following. So if each party is going to, when it receives the n minus t votes, what is a party going to do? The first thing they're going to do is wait for n minus 2t fragments that match the Merkle root. Why is this going to work? Well, remember, by the many echoes property, if we've gotten to this stage, like somebody has voted for this Merkle root, right? Which means that there were n minus some party received n minus t echoes. Among them, there must have been n minus 2t echoes that actually came from honest parties. And what are those honest parties going to do? They're also going to be echoing their fragments. So there's got to be, so if I get to this stage where I've received n minus t votes, for sure the n minus 2t honest parties have echoed fragments that are consistent with the Merkle tree. So I can afford to wait for them. I'm guaranteed that they will arrive eventually.
I have a question.
Yes.
So here it seems the broadcaster is sending the fragments once, and then parties are sending it back again. So no matter how efficient coding we use, let's say we have a coding scheme somehow which doesn't do any blow up, then we're anyway sending the message twice, right? First, the broadcaster is sending once.
Okay, let me come back to that. Okay, I'll come back to that in the next slide. So I've gotten my n minus 2t fragments, and they're consistent with the Merkle root. I'm going to run the decoding algorithm to get some message, let's call it m prime. I'm going to re-encode m prime into fragments all over again. So I can compute all the fragments associated with m prime. And then I'm going to recompute a Merkle tree with all of these fragments. And I'm going to test if what I get is consistent with the Merkle root that was output here. Because why am I doing this? So why is this done? What this is done is really, I came up with a very fancy name for this because it doesn't seem to have a name. I'll call this is kind of a post facto guard against inconsistent fragments. So why am I calling this that? All through this protocol, nobody has done any consistency checking whatsoever to make sure when they receive and echo a fragment, who knows if this is really a fragment of some Reed-Solomon code word. It may or may not be. It's just something I got and I'm echoing it, right? Who's to say if the sender is corrupt, he might actually just, commit to a vector of random strings that are not that don't form a code word. And so what are you supposed to do when that happens, right? Well, what you do is you just treat the sender, at this point in the protocol, you'll detect that he did that, and you will basically treat his message as being garbage and ignore it. And the nice property is that if you choose to do that, so will everybody else. So either all parties will see that this vector that was committed to was actually a commitment to a code word, or it wasn't, and we'll all agree on that, whether it was or it wasn't. This wasn't in your original paper, I don't think. This kind of post facto guard. There's
Somebody must have verified something nevertheless.
You verified something somewhere along the line, but in fact there were extras. So it wasn't. So this particular way of doing things is a little bit simpler and has fewer rounds and a little bit constant lower complexity. And this idea of kind of this post facto guard, I mean, I think it's a cute idea, but and it's appeared like. I've seen it in like 3 different papers. One's SODS BC, which I don't know too much about, and then there's this Dumbo MVBA paper, and dispersed ledger. This is the first place I ran across it, was this dispersed ledger, but after the fact I noticed that actually it appears in a couple of different places. It's kind of a nice little trick. It's not like, going to change the world, but it's a nice trick to know about. Because there are applications where you need more. Maybe you need to like send out fragments along with proofs that these fragments really do are consistent with the code word, right? So, but for this particular application, you don't need that at all. It's perfectly okay if you just like detect that these were bogus fragments like at the end. You don't have to like go out of your way to do any extra checking, which is nice because then it lets us use kind of whatever efficient erasure coding scheme we want. We don't need an erasure coding scheme. We don't need to use KZG commitments. We don't need to do anything fancy. Just any vector commitment and any erasure code will do. So is this practical? Well, so now I'm going to answer Saurav's question about communication complexity. What is it? So each party is going to echo. Well, so when he does the echoing, there's going to be n fragments sent to each party, right? This is what each party does, right? He's going to send n fragments out over the network. Each of these are of this size. So it's going to be 3 times the message length. That's what each receiver does during the echo. The sender is going to transmit also an additional 3 m bits. So if we're measuring communication complexity as just the sum of all bits transmitted, this just adds in once, right? The sender just does this once. Every other party does this many times. So you get n times this plus one of these. So it's kind of balanced, even though the sender is like sending twice as many bits as everybody else. So it's kind of annoying. There's another trick which I haven't seen it before, but I've used it in a couple of places, which is kind of nice. What you can do is instead of using an n minus 2t out of n code, you can just subtract 1 from both parameters. And so basically, there's going to be n minus 1 fragments instead of n. The sender is going to transmit to all the other n minus 1 parties their fragments out of this code. And then he's just going to stop. And then his role is over. He's not going to echo anything. He's not going to do anything. So he's transmitted once, and reconstructing the message out of these fragments is a job for the other n minus 1 parties. For small n, you get slightly less optimal overall communication complexity, but for large n, there's no real difference, and then you get perfect balance. Every party is echoing. Yeah, go ahead.
Many people want to treat the sender as an outside client.
You can do that too. Yeah.
Then
I guess none of this matters.
Then it's still n.
Then it's still which is fine. Okay. Yeah. In the applications I have in mind, like for leader-based atomic broadcast protocols, the sender will typically be one of the n parties.
Transaction comes from the client.
No, transactions come from the client, but blocks come from the leader. So, okay. So let me go through an example, because sometimes I think that people think of these erasure codes as some exotic, expensive beast that you would never use in practice, right? And I wondered that myself. So I was wondering, like, is this all just, kind of science fiction that you would never implement? So I did some micro benchmarking. I didn't like implement a real system or anything like that. But okay, so here's my example. I set n equal to 100 and t equals 33, and a message size of 4 megabytes, so something reasonably big. For purposes of putting this all together in a minute, I'll assume a 1 gigabit per second network. So that's the upload and download speed onto the network. So these were all done with my MacBook down here. There's a nice library on GitHub, which is it's an erasure coding library written in Rust. You have to look through the document. It's a nice culmination of a lot of theory and practice. So there were some papers written over the last 10 years that really kind of push the envelope on terms of the theory of erasure coding a little bit. I mean, it's still, all polynomial interpolation and whatnot, but they have special tricks, special types of FFTs over special domains. But all of this was just like on paper. And then thanks to, the beauty of GitHub and this kind of sharing, there's been several iterations of libraries. People have taken like a first implementation and then the second implementation. This one is, it's SIMD, so it's written carefully to exploit AVX instructions on a x86 machine and the Neon instructions on my MacBook, and it's really impressive. So the time to encode a 4 megabyte block using these parameters is like 3 milliseconds. Time to decode, a little bit more, 13 milliseconds. Pretty good, but these numbers only mean something in relation to other numbers. Like, is this expensive? Well, I don't know. Is it expensive relative to the cost of transmitting and downloading the data? My answer is no, it's not at all, right? So there's also a lot of hashing going on here. We have to do all this hashing for the Merkle trees. Time to hash everything you need is, for both sender and receiver, is going to be 6 milliseconds. Again, just using my laptop here. And then let's look at data transmission time. So here I'm assuming this kind of like pretty conservative 1 gigabit per second network. So the time for a party to transmit 12 megabytes, right? It's 3 times the message size, right? My message size here is 4 megabytes. Everything gets blown up by this factor of 3. So if I did my arithmetic correctly, this turns into 96 milliseconds. So you can see that, the time you spend doing all this hashing and coding and decoding is not very much compared to the time you spend just uploading and downloading data off of the network. So it's faster than the network, so it's fine. There's no reason not to do any of this. Here's where I get a little bit maybe controversial. Like, how would you do this otherwise? Like, I know projects that are out there, they don't use any of this erasure coding stuff. They just send it all out. Like, this is what we did at Dfinity when I was there. You've got a block proposer who's just going to send the same 4 megabyte block to everybody. I'm not an I'm a theoretical computer scientist, I guess, but I know enough and I've talked to enough people to figure out there is no magic way to do this really on a standard, internet setup. You're just going to literally send the same message to everybody 100 times, and there's no like magic to avoid that. There are alternatives. But if you do this, right, just over point-to-point networks, you open 100 TSL connections and you send the same damn thing 100 times, right? And it's going to take you, over 3 seconds to do that, just to upload the data onto your network. So yeah, it's already, a win. Let me just say one more thing before I take a question on this controversial point, which is you could do other things like gossip protocols and whatnot, which those create other problems, though. I mean, first of all, it's the latency is going to be quite a bit higher because it has to go through several rounds to reach everybody. And then you also have security issues, like how many people are you gossiping to, and what's the probability of hitting corrupt subset of parties when you gossip? So, question?
Did that include proving time? And you didn't?
Proving? There is no proofs. Hashing. There's only hashing.
Just Merkle proofs.
Just Merkle. Yeah.
Okay. I thought you said there was also some proof that you'd encoded the file correctly.
No, those were just Merkle proofs.
It's all Merkle proofs.
Huh? It's all Merkle proofs. And I went out of my way to say that, if you weren't paying attention, young man, I went out of my way to say that we don't need any proofs of consistency other than just a post facto Merkle proof check at the end, as opposed to doing like KZG commitments and doing some kind of proof that I've evaluated a polynomial at a point or something, right? That's kind of the Dunk sharding vision, right? Which is using these kind of proofs of, yeah. That's why I wanted to like shake you up a little bit and say you don't, for some applications, you just don't need anything like that, which opens up a lot of opportunities because then you can use Reed-Solomon SIMD codes instead of some super slow KZG type stuff. Yeah. Question?
Another comment to compare the last item there, the 3 seconds, right? Mm-hmm. Our predecessors, Castro and Liskov, They use the hardware multicast, IP multicast, to UDP
yes.
for this stuff. Right?
But nobody really uses this, right?
Absolutely not.
Right. So yeah.
No,
Or
just
you're on a
mention-
LAN or something, I guess.
because they thought it's too and this was restricted to a LAN,
Yeah.
obviously.
Yeah. So anyway, so I haven't gotten to any new results yet. I just giving you the background. Yeah. First step. So Thomas had his paper where we reduced 3 to 2. I'll show you that, and then I'll show you how to reduce 2 to 1.5. It's just kind of fun and it's all simple. I hope you think, like, this is really simple. I had a feeling giving this talk that you all will just kind of laugh at me because it's all just kind of simple. So here's Locher's idea. And again, I think the most interesting thing here is just asking the question. The answers are not that difficult, but the fact that nobody even asked this question is kind of weird. So why we're using n minus 2, why we have a reconstruction threshold of n minus 2t, so roughly n over 3. Why not use n minus t? We have n minus t honest parties. You would think that we could somehow use all of them, right? So we're not really using them. Because if you do this, then you need n minus t fragments to recover m, so you need more fragments, so it's harder to make sure that you really get them all. But if you can do that, then the nice thing is the fragments are half the size as they were before, 1.5 instead of 3. So how do you actually do this? Well, here's Thomas's idea for getting this down to 2. I'm going to present it in a simplified way that has a bit more, the number of rounds is a bit too high, but it's easier to convey the basic idea. It's 1 or 2 extra rounds of communication here. So to simplify things, we're just going to, as before, the sender is going to form a Merkle tree with the roots, with the leaves being fragments, but now with a code with these parameters. And then we're just going to, in the simplified version of the protocol, we're just going to reliably broadcast the root of the Merkle tree. And then only when we've finished that, we'll proceed to the next step. We're also going to disseminate the fragments to each PI, but each party is going to, because we're trying to be a little bit stingy on communication complexity, each PI is just going to hold that in his pocket until this BRCA broadcast is finished, and we're sure that we all agree on what the root of this Merkle tree is. Because I could get a fragment associated with a different Merkle tree, and if I broadcast that, I've just kind of wasted some bandwidth. So I'm going to be careful not to broadcast my fragment until I know I've got a fragment associated with the right Merkle tree. So then only after I know what R is and I deliver it, then I echo it if it matches, right? If it's consistent with that. Now, when P receives valid, so now again, each party is going to receive valid fragments of n minus t parties, and they're going to go do the same thing as before. So now I'm going to carefully name these parties, right? So I've got a set of n minus t parties. Let's call them, P sub j for some subset j of parties. As before, PI is going to reconstruct M and all the fragments and apply my post facto consistency guard. He's going to output M, but now he's going to help his comrades out. He's computed all the fragments, right, for everybody. He received n minus t, but now he's got n fragments, and he's going to carefully just send his fragments back to the parties from whom he didn't receive a fragment. That's the whole idea for this thing. There's more. I won't disappoint you, there's more. A party who receives kind of this backup fragment, he might have not received anything from the sender, or he might have received a fragment for the wrong route if the sender was equivocating on the Merkle tree route. So he's going to wait around, and then finally, if he gets either a fragment from the sender that's the right one, or a backup fragment from one of his colleagues, then he will echo this thing. So this guarantees that all honest parties will eventually echo their fragment. Remember, for completeness, we want it to be the case that if any party outputs the message, then all parties do. So I've received n minus t fragments and output the message, but there's no guarantee that anybody else is going to receive these n minus t fragments unless I help them out. So I'm going to make sure that so if I output something, I'll make sure that all honest parties eventually get their fragment, which they can then echo, which will make sure that all n minus t honest parties are eventually echoing their fragment. And so every honest party will eventually collect n minus t fragments and eventually output m. So that's my argument here. All honest parties eventually echo their fragment, so all honest parties output m. What are the bits sent for each receiver? Well, in the echo, everybody sends one fragment to n parties. So this is the size of a fragment, sending it to n parties as part of the echo. So that's 1.5 times m. For the backups, you see we're cleverly only sending backups to 1/3 of the parties. basically, because only to parties from which we didn't receive a fragment in the first place. So when you add it all up, you get 2m. Yes, the wonder of grade school arithmetic. Yes, so that's that. But that's clearly not the end of the story. This is too simple, so we have to do something more complicated to get to 1.5. You see there's a lot of waste here. Obviously, there's room for improvement because I'm sending my backup to everybody. I'm sending backups to a lot of parties, and in fact, if I'm missing if I don't have a fragment to echo, I'm receiving backups from many parties, right? So there's a lot of there's a lot of repeated stuff being echoed around. So can we be more stingy on what we send around? So here's how we go from 2 to 1.5. Again, a bit simplified. We're going to again use the same erasure code with the same parameters. Each fragment will have size. Now I'm going to be a little bit careful here. So each fragment will have size 3/2 m over n. And in this part of the presentation, you might start to worry about what happens when m is not really big. So there's always no matter how big or small m is, you can be sure that if you use, say, just a standard Reed-Solomon code of some time, it's going to be this plus some log n term is going to be the size. Then we're going to use another erasure code with parameters that were used for the naive Braca to encode fragments into mini-fragments. So each mini-fragment, then, you just divide by n and multiply by 3, you get the size of a fragment, and we still have this log n term. So you might complain, well, this is all going to be meaningless if m is not very big, and that's true, but anyway, it's all going to be absorbed into the n squared log n term that we're not anyway worried about anyway. So in practice, you would probably want to not use this scheme except for a very large m, but I'll show you an example. It's not that bad either in practice. So at a high level, we're going to use Braca, just like before, to broadcast the root of a Merkle tree. Now it's actually a 2-level Merkle tree. I won't go into all the details on here, but we're basically taking a message, encoding it into fragments. I can draw a little picture here. I encode it into n fragments, and then each of these fragments is going to be encoded into a mini-fragment. And now that's my 2-level, and then these guys here are going to be the leaves of a Merkle tree. And I'm gonna pass around, I'm gonna disseminate the root of this Merkle tree here. I'm only going to send fragments to parties. At least the sender is going to send fragments. So for parties to verify their fragment, what they're going to have to do is encode the fragment into mini-fragments and then check that against this Merkle tree. So there's a little bit of extra hashing going on, but it's all okay. So here's like a simplified version of the whole protocol. The sender is going to use Braca to broadcast the root of our Merkle tree. He's going to disseminate fragments and proofs to each party. Then only after R is delivered, each party is going to do the following. After R is delivered, each party is going to echo its fragment and the proof of its fragment. Then, as before, he's going to wait until he receives n minus t fragments from other parties. Now we just have to make sure that everybody else is going to get n minus t fragments as well. And we're going to do a little bit of waiting here. So PI is going to reconstruct M and all the fragments and apply the consistency guard as usual. And then he's going to send a backup mini fragment. So I've got all the fragments, and I'm going to encode each fragment into mini fragments. And then I'm going to send to each other party the mini fragment it needs from me to get its fragment that it's hopefully waiting for. So instead of sending a fragment back, I'm just sending a mini fragment, which is where you cut down that extra 1/2 term. So if I'm sending a mini fragment to all parties, then any party who is not holding a fragment can collect n minus 2t. He'll be sure to again just by the many echoes property here. If I receive fragments from these parties, I know that then we're sure that n minus 2t parties are sending backup mini fragments. Each party PJ will echo its fragment when it collects those mini fragments, if it hasn't already. Okay, and then so that's how these mini fragments are used. But notice I haven't actually output a message yet. So before I do that, I need a little bit of extra synchronization. And in this case, you can get by pretty cheaply. Just I've done all this stuff. I've got my n-t fragments. I've reconstructed the message. I've sent backup mini fragments. And I'm not quite ready to output the message yet. I'm going to send a ready message to everybody. And then I'm going to wait for n-t ready messages from everybody else. And only then do I output the message. And what does that buy you? Now I've output my message. So it better be the case that I can argue that everybody will eventually output their message, right, to maintain completeness. So if I get to this point where I've received n-t ready messages, that means that out of these, n-2t honest parties have done the same thing. They've reconstructed M and sent backup fragments to everybody, right? So that means that all honest parties will eventually receive these n-2t mini fragments if they need them, which will allow them to reconstruct their fragment and then echo their fragment. So all honest parties will eventually reconstruct M and also send their ready messages. Eventually, all honest parties will output M. All honest parties will eventually send ready messages, so that makes n-t, so we're not going to get stuck. Yes, so that's the whole thing. Bits sent per receiver. So the same, for the echoing, we have the same as before. And then for the backups, well, these are all mini fragments now, so they're like an order of magnitude smaller. So it's really like not there. It's a lower order term that we're not going to worry about. The next I have up is some comments about a few things. Round complexity, there's definitely like something extra there. There's this extra round of waiting to make sure that I don't stick my neck out too far ahead of other parties, right? There's this step of, it seemed like a small thing, but it's really there and it's hard to get rid of. Like I really have to make sure that not only have I gotten to this stage, but n-2t honest parties have gotten to the same stage as me before I'm ready to commit to delivering this message.
So why was it that came up here and not in the previous protocol?
Because I was sending out whole fragments. Here I have to make sure that there are because I alone can fix it. I alone am sending fragments to everybody who could possibly be missing a fragment. So I'm sure that everybody who needs a fragment will get it. Here I'm not so sure because I'm only sending one piece of a fragment, and I got to make sure that a bunch of other people are sending pieces of this fragment. If you're careful about this, so Braca, kind of in the optimistic path where the sender is honest, has 3 rounds of communication. Here we get it 4. That's the best way you can figure out how to do. You can get it down to 3 rounds on kind of an optimistic variant where the problem arises where if you have again, the idea is you're going to send out your fragment before you're really sure that it's safe to send it out because you haven't agreed on the Merkle route yet. If you do that, you could have the communication complexity might be a little bit higher, but that'll only happen because you have a corrupt kind of equivocating sender. So that'll cause some extra communication at the cost of a round in the worst case, but he'll be caught. I mean, especially if you attach signatures to things, you can implicate the sender as a equivocating sender, and maybe there are economic incentives to prevent that. Going back to my little example, same parameters as before. There's a lot more hashing and a lot more coding going on, so you might worry that, I was worried that this is going to be like kind of silly. So in this setting with a 4 megabyte size and this many parties, like each fragment is like 60 kilobytes. Mini fragments are still like almost 2 kilobytes, so not like too tiny to make it like impractical to be sending these all around. In terms of erasure encoding, like you have to encode a message into fragments. Interesting, so before this took 3 milliseconds. It turns out, for reasons I don't fully understand, when you increase the reconstruction threshold but keep n the same, it's actually faster to do the encoding and decoding.
I believe it may be using systematic code. So if
it's a systematic code, then for sure, yeah. And it is a systematic code, so maybe, okay, it's not surprising. Okay, so, and then you have to encode, the sender anyway is going to have to encode all the fragments into mini fragments. That takes 3.9 milliseconds, so all in all, you do spend a bit more time. Time to decode the messages from fragments. Again, the decoding is also faster. This was using, I think, a random subset of fragments, so I'm not cheating by using just a systematic code. I think even like I'm using all the the parity check ones. Yeah, I think there's a switch you can set in this code. And then you have to decode a fragment. If you need to, you don't always have to do this, but if you're missing a fragment, you'll have to decode fragments from mini fragments. That's very quick. Hashing time also increases. There's a lot more hashing because you have this double tree of, so there's a lot of hashing. It jumps up to 12 from 6. Data transmission time obviously falls in half. And again, there's and with these numbers, I worked out exactly, there's these lower order terms, but they're really not there. They're within a couple of percentage points of the asymptotics at this thing. Open question is 1.5 optimal. I don't know. Like I said, there's some partial results. It would be really cool to see some results. I want to close with an application. I've kind of talked about this a little bit. Some applications of reliable broadcast, you have everybody broadcasting all at once, and then you gather together these broadcasts somehow. And for these, balanced communication isn't so important because everybody's working symmetrically, right? But for if you take PBFT, what are some examples of this? PBFT, hot stuff, they all kind of conveniently actually just ignore the problem of how you actually disseminate these blocks. They assume there's some way to do it, but they don't actually talk about how to do it. But if you actually do try to do it, it becomes actually a bottleneck because you have this leader who's trying to push out megabytes of stuff to 100 parties, and he gets bottlenecked by his network bandwidth. This is a phenomenon that, so is anybody here a hot stuff cheerleader? I don't know. So I get a little bit freaked out sometimes by how there's all these papers in the literature that are hyper-focused on reducing the communication complexity from n squared to linear, when that's not even the bottleneck in the system. The bottleneck in the system is disseminating these large blocks to everybody. The rest of it just doesn't really matter, unless you have 10,000 nodes in your system or something like that. And people have noticed this over the years. There's a nice paper, Honey Badger, some of you have seen this. They also do experiments, and they say, well, here's hot stuff, and here's our super slow Honey Badger that works in the asynchronous model, and it actually gets much better throughput because the bottleneck at the leader. There's another less well-known paper by some folks who used to work at IBM in Zurich, I think, Mir BFT. They made the same observation and came up with a completely other way of dealing with this problem. Also, the whole DAG stuff, if you read their papers, it's all predicated on the fact that, there's a bottleneck at the leader, so we have to get rid of the leader. And there's a lot of nice reasons. I like this work, and it's great, but the argument that because there's a bottleneck at the leader, you have to get rid of the leader seems a little bit misguided. What you can do is just remove the bottleneck from the leader, but keep the leader in place. So we don't need to abandon leader-based protocols. What you can do is use a reliable broadcast with balanced communication to relieve the bottleneck at the leader. So this way, the leader is just disseminating fragments out to parties, and then they're helping, because of balanced communication, everybody will get the block from the leader. Now, I mentioned for our particular protocol, there's 4 rounds to disseminate, to run this protocol. But if you're careful and clever, you can maybe, bolt this reliable broadcast protocol into an existing BFT protocol in such a way that you actually don't increase the optimistic latency. And so as to closing with a shameless plug for another paper, which I was thinking about presenting here, but I'm not. There's a beautiful, not my work, the beautiful paper is Simplex, which is it's a nice PBFT-like protocol. Works in the partially synchronous model, like PBFT. And it's such a beautiful, simple protocol. I don't really know why you would ever learn or teach another protocol in this space. I mean, in the partially synchronous leader-based protocol, it's such a beautiful, simple protocol. And then in this follow-up paper that I did, I sing the praises of this protocol. In addition to that, I kind of tweak it a bit and show so they're not really worried too much about communication complexity, more like latency. And I show that you can bolt on different flavors of reliable broadcast with balanced communication, so that actually you can get you don't have to increase the latency. Their protocol has optimal latency on a couple of different metrics, and you can bolt on a more efficient, balanced broadcast protocol without increasing the latency whatsoever, which is really nice, and to get all the benefits of this. So I did some my experiments in this space are running micro benchmarks and doing back of the envelope calculations to see that if nothing else is really weird, then this should predict the behavior of the system. So somewhat optimistically, if the leader is honest, and this is for a version of this with a stable leader that runs for a while, you can get 80 megabytes per second throughput, which in this space it seems like people take like a half a yeah. So this is quite good. And then you can get and the latencies are pretty good too. So that's my claim, is that you don't necessarily we don't have to give up altogether on leader-based protocols. There's advantages and disadvantages. The nice thing about leader-based protocols is when the leader is honest, you can really, hit the gas pedal and go really fast. But the problem is once the leader is broken, it can take, maybe a couple of seconds to recover and switch to a new leader, which the DAG-based BFT protocols don't have that problem. And of course, you have problems with the leader who might be censoring or not fairly scheduling transactions. So there are trade-offs there. Final questions, complaints?
So it seems that you're using two-dimensional Reed-Solomon code, where you first get a row but you get 1 point. You also get a column, and then you're disseminating the column. So somehow I see similarities there.
Yeah. Could you? Yeah, I don't know if there's. Yeah, I didn't really think of it that way, but you could. I don't know.
All this VSS with bivariate polynomials have this structure. You have this. You take this whole long message, convert it into a matrix, give 1 row, 1 column, and then try to help others reconstruct 1 column.
That's true. It has a similar flavor, and maybe there's a way of thinking about it along those lines. But I think this is going to be better, because I think if you're really working with these bivariate polynomials, you're going to be stuck in the slow lane doing all kinds of finite field arithmetic, as opposed to using unless they're really good bivariate.
I want to think of them as simple black box codes, not too much as they'll probably still work with smaller fields, and then.
Yeah, I'm just saying the implementation's out there for really fast. And maybe there's a nice way of thinking about it that way that leads to some other results.
And another, probably not very important, but you can, although you have n square log n lambda, you can do it n square.
So you're saying, can you get rid of the log n like you do in these other settings? That's a good question. I actually don't know. I thought about that a little bit.
Okay.
I made sure I understood your techniques, and there's something going on there that I don't see how to solve. You can call it an open problem if you like. Maybe there's something you can do there. I'm not too worried about it, because for the parameter examples I showed you, that second order term is you can't even see it in the final numbers. So I'm not sure. Yeah.
I have a question or a comment on the reliable broadcast.
Which one?
The reliable broadcast, the Bracha broadcast tool itself, right?
Yes.
Because it does a lot of the work to make sure that everybody actually receives the message, what can be called totality, right? You output the message, I'm eventually outputting the message as well. And I think most practical systems, they just rely on the fact that they are going to do another round in the future, and in this other round in the future, I am going to realize that I may have missed something from the previous round, like I have missed the previous reliable broadcast.
And then you're going to ask other people
delivery,
for it?
and then I'm going to ask other people for what they have delivered, what I might have missed, and so this is not going to come in. This is the practical optimization.
This is right. So this is so I've had these discussions with Surab and other people. Why are these people doing this? Why do they hate on erasure code so much? And they insist on doing it. Well, because you're right. So you could just ask for it, right? But okay. So 2 things. One is, isn't this opening you up to a DOS attack? You could have, if n over 3 parties are corrupt, you could have these n over 3 parties asking everybody for their block all the time. And then how are you gonna?
Well, there is yet another exception mechanism to block them out and kick them out of the protocol, right?
How do you know? Okay, so you have to come up with some.
Because they have asked too many times.
Okay, I guess you could do something like that. Or I've thought but I think there's maybe a nice if you're not worried about. So first of all, that doesn't solve the balanced communication problem either. So that's
no. That remains. So for this, erasure codes are still good.
Right. So they're good for that. But even if you're not worried about balance, like you're in the DAG writer kind of protocol, where anyway you don't worry about balance, I still think that there are variations on this protocol where instead of being polled for missing blocks, just poll for missing. I can ask for fragments, right? I can because the problem with this polling is too. I have to ask several parties. for a block because I don't know who's going to respond, and they're all going to respond, and so it's also very wasteful, right? I could instead like ask everybody for a fragment, and they could send me a fragment, and then this. I don't know if anybody's proposed this in a practical system. Like you could have like a pull mechanism, like what you're talking about for missing blocks, but base it on erasure codes as well.
Yeah.
If I'm missing a block, I can just ask everybody for a fragment, and they'll give me a fragment.
Napster might be doing it. What is it called? They're doing this, right? What are these? BitTorrents, right? They're doing this, right? Yeah.
Okay.
That happens all the time, yeah.
It happens all the time, okay.
Yeah.
But I
Well,
also
maybe
think that
not
you
here.
can actually get by, you can use this fragment and mini fragment business too to even like cut down the
Yeah.
constants a little bit more if you want to.
As a technical comment, my initial suggestion to use 2t+1 in the last round for running with n much bigger than 3f or 3t, this could be done, right? We can have
Sure.
n equals 1000 and we tolerate only 10.
Yeah.
N equals t equals 10. In this case, this optimization will not work, right? This you have to go to n minus t to 990 here, nevertheless, probably.
But isn't it better to use n minus t to get better,
of course you have to-
better erasure code parameters?
You would, right? Okay,
Yeah,
it's
okay.
opening up
Yeah.
another
Okay.
dimension.
It's another dimension.
Yeah, few people told me that they don't. Right now, many industry uses consistent broadcast. Simply send a message, collects signatures,
Yeah.
and they didn't want to do any coding because of this 3x blow up. Maybe one, but they also.
But that's what I claim though too. I think it's still right. I agree that you can do that. You can use consistent broadcast, but then use coding for the backup pulling,
Yes.
for the pulling the backups. Wouldn't that be better
My
on every
impression is
metric? Unless you're
people just want to have a backup. They never want to use it. If there is something bad, they'll start phoning around and then say, "Oh, there is."
Yeah, but it could be that at some time they actually calculate the whole cost, right? And then there's a story from erasure coded storage, like in cloud storage, like Amazon S3 and friends, right? They were initially like replicating stuff, like we were doing this erasure coded thing that you cited even on. They said, "Oh, we should do erasure coding," right? And guess what? 5 years later, Microsoft Research wrote, "Oh, they're doing erasure code now," and all of those like papers, right? Because of the cost, like they had to buy fewer disks for the cloud storage, for object storage.
right.
All right. Thanks again, Victor.
Thank you.